Can you see the screen?
No,
No?
not. Yeah, maybe now.
So yes or no? So can you see the slides?
Just a second. Oh, uh, we can see your slides now.
Okay, perfect.
Thanks.
Okay, so as far as I remember, you had two nice talks from Pallavi about basically single winner elections and then multi-winner elections. Um, and today I want to speak about participatory budgeting, which is a subject that relates, as Pallavi said, to multi-winner elections. In a way, it generalizes it. So the way I view like the main branch of voting theory in computational social choice is that the simplest setting is single winner elections. Then there is the generalization to multi-winner elections, and this can be generalized further to participatory budgeting. So formally, single winner elections, you select one winner from the election. So K, the number of winners is one, and the cost of each winner is one. So you have like a budget of one, and each candidate costs you one. So you have to select one candidate. This is single winner elections, like when you select a president. And then multi-winner elections generalizes it in the form that each candidate still costs just one, but now you have a budget of K. So basically you select K candidates because each one of them costs one. And participatory budgeting generalizes this further because now you can view it as you have like a general K, which is like the budget that you have, like the number of seats in the parliament for multi-winner elections, or the number of committee members that you want to select. But here it could be a number of dollars or whatever. But now the generalization for multi-winner elections is such that the cost of each candidate is not one, but could be arbitrary. So you select candidates where each one of them can cost differently, and you want to select good candidates that still fulfill this K budget requirement. So my personal point of view is that I did some work on multi-winner elections, and I found it very interesting. And I thought that the computational and social choice community arrived to some good understanding of multi-winner elections. And then some friend told me about participatory budgeting, and I realized quite quickly that this is really a generalization of multi-winner elections. But I was quite surprised to see that the way that participatory budgeting is done in cities is very, very simple and it feels suboptimal to me. And then I started to dig further into trying to find better ways for doing participatory budgeting, building upon the knowledge that the computational and social choice community have acquired for multi-winner elections. So what is participatory budgeting? This was first done in Brazil. You see below I think it's the Workers' Party of Brazil, or some neighborhood of in Brazil. The main idea is that you take a city, and a city shall decide how to spend its money on certain projects. And usually the way that this is done is that the mayor of the city with some committee, they decide how to spend the city money, the mutual funds of the city. And participatory budgeting tries to do this in a direct democracy participatory way. So usually this is done in the following way. There is the total budget of the city for the coming year, for example, and then you take 1% or 2% of the total budget, and you do like an election process in which first citizens of the city can suggest projects to fund, and then you acquire the costs for each of these projects. And then you do a second stage, which is the phase that I'm interested in, that corresponds more to the standard study in computational and social choice, in which there is an election where people come to the ballot booth and they describe their preferences among these projects that were suggested. And then all these ballots come to some aggregation method, and then the city decides, this algorithm decides which of the projects to fund. Maybe the most like the biggest example in which participatory budgeting is happening now is in Paris, Paris Budget Participatif, in which something like 100 million euros is being decided by the city in this participatory budgeting election kind of process. So let me give you an example to make the setting of participatory budgeting clearer. So this is an example from Cambridge in 2015. And basically people, citizens of Cambridge came to the ballot booth and they saw something like this. This is only like one page of the ballot that they saw. There are more projects. Here you see only 10 projects. And you see that each project has its name. For example, if you see on the top right, you see these bike repair stations. So this is the name of the project, and the cost of the project is $1,200. And there is some textual explanation of what is this project about. And then basically, if I go back to the rules, you see that each voter should have marked at most 5 projects. So basically, people could see all of the projects that were suggested, and they mark at most 5 of them. So these are approval ballots, because basically from the set of projects, each one selects at most 5 projects to approve. And then the city said that they have $500,000 to spend on this whole process of participatory budgeting. So they aggregated all these ballots. The way that they did it in Cambridge, which is still the most popular way in the world to do participatory budgeting, they basically took all of the projects and count for each one of them how many voters marked them, how many voters approved each of the projects. So for example, you see that there was a project of planting 100 new trees, and this got marked by 1,441 residents of Cambridge, and the cost of the project is as written here. And then there was the second most popular project was the CLC computers, which I'm not sure what is CLC, and this got the votes of 1,110 and so on. And then basically what the algorithm does, it takes all of the ballots, it computes how many votes each one of the project got, and then you order the project by this number of votes in decreasing order, and you start to fund until you reach the point that there is not enough money left. So for this example, it was supposed to be just after bike repair stations, in which the total cumulative project cost was almost $500,000. And then if you also decide on funding this free outdoor Wi-Fi, then it will go over the limit. So in Cambridge, the city said, okay, we can also fund this, and then they went a little bit over the limit. But this very simplistic, greedy approval kind of algorithm, this is what was used in Cambridge and also still in Paris and in basically most of the places on Earth. So this is by far the most popular algorithm. And if you recall, like the setting and also the setting of multi-winner elections, you see that in multi-winner election there are many, many other algorithms that have some nice properties. And then my first impression is that it must be the case that the result that we have in multi-winner elections in computational and social choice could be generalized to this more general framework of participatory budgeting. And that if we really are able as a community to do this, if we can lift the nice result that we have and the nice rules that we know how to select committees and the multi-winner voting settings to the participatory budgeting setting, then this will be really useful, because participatory budgeting is just a formal generalization of multi-winner elections on the one hand, and on the other hand, it's really used in the world to decide on real money and real projects that make impact for residents of cities. So I thought that the fact that Paris and other cities use this very simplistic, greedy approval algorithm is suboptimal in a very painful way. Okay, if there are any questions, then I cannot see you because I'm sharing, but you can ask.
Stating the objective of the study. Could tell us once.
I can hear you really low, so.
May I know the object objective of the study, like the definition of participatory budgeting,
Okay,
what
sure. Yeah,
we are trying to do.
so I will come to this in a second. Thanks. Yeah, so this is the way in which this is done usually, but let me give you the formal definition. So there are several variants depending on basically how you elicit the preferences from the voters. But the formal definition of participatory budgeting, at least this variant of indivisible participatory budgeting, is as follows. So you have a set of items. This is similar to what in multi-winner election called candidates or alternatives, but here you can call it items or projects, but it's the same. So here it's just the P1 to PM. And now each one of these items or projects has a cost. So there is like a cost function that assigns to each one of the projects some monetary cost. So this is one thing that you have. And the second thing that you have is voters. So in the example before, we used approval ballots, which means that basically each voter gives you a subset of the items that the voter approves. But there are other elicitation or ballot types that I will speak about later. And then the third thing that you have is some limit, like a budget limit, which is similar to the size of the committee in multi-winner elections, but really just the total amount of dollars that the city has to spend for the whole process. And now basically what we're looking for an aggregation algorithm that takes as input the items with their costs, the budget limit, and the votes, and outputs a bundle. And the bundle is just a set of projects such that the total cost of this project is not above the budget limit that we have. And this bundle should be good. So what does it mean good? Informally, it's like in single winner elections, you want the voting algorithm to be such that it will select a good president or a good single winner. And in multi-winner elections, you want the algorithm to be good in the sense that it will select committees that are good in some way, so they respect the voters' preferences in some appropriate way. And in participatory budgeting, this is the same. I mean, the informal setting is that you want the output bundle, like the output set of projects that the city will fund eventually, to be appropriate to the voters' preferences. And how exactly to make this a mathematical objective or mathematical notion, this is something that we shall decide. And I will try to show several objectives that we want to optimize or to achieve, and then how to achieve them from an algorithmic point of view. Okay, so I hope that this makes the formal setting clear, and also that this is really a simple, a straightforward generalization of multi-winner elections, because multi-winner elections is just that, this cost function will be just the unit function. So for each project, the cost will be 1, and then this is really exactly equivalent to multi-winner elections. But now the cost could be different, so then this is a different, more generalized setting. Okay. So let me jump into some objective functions and some corresponding algorithms. So the first one is basically from this paper that we try to offer a principled approach to defining the objective that we want from these kind of algorithms. And the approach is a utilitarian approach, or a satisfaction-based approach, and it works in the following way. So consider some voter, and let's say that this voter, so say that there are projects A, B, C, D, E. Okay, so there are 5 projects, A, B, C, D, E. And now consider a voter, I call it here my vote, that approves A, B, and D. So when I come to the ballot booth, I mark the project A, B, and D, but I don't mark the project C and E. And now what I want to define like the satisfaction or the happiness level of this voter from any possible bundle that the algorithm may output. So if you consider this abstractly, basically the algorithm shall take votes that look like this vote, and shall aggregate these votes and output some bundle. and now look at all of the 2 to the number of projects bundles that are possible for the algorithm to compute, to output. And what I want for each one of these possibilities to define some numeric value that will be like the total happiness or the total utility that this bundle gives to the society. And one way to do this is to define for each possible bundle what is the utility that this bundle gives to a single vote, and then to define the utility that the bundle has as a whole as the sum of utility that is given to all of the voters. And this is what we try to do here. Basically, we defined a good algorithm to be an algorithm that maximizes, that basically finds a bundle, which is a set of projects that respect the budget limit, and that maximizes the total satisfaction of the society, where total satisfaction means the sum of satisfaction of all voters from this bundle. And now it depends, and now the specific definition depends on what is the definition of satisfaction that one voter gets from a specific bundle. So there are several ways to define this, and this is what we try to do in this paper, basically to define several satisfaction or happiness functions, and for each one of them to see whether we can find a good algorithm that maximizes the total satisfaction based on this individual satisfaction function for each vote. So for example, if there is a vote that marks ABD and the output bundle is ACD, then one simple way to define the satisfaction of this voter from this possible bundle is to say that, okay, the satisfaction is 2/3, because, or actually 2, because we can just count the number of projects that this voter wanted, and it was really funded by this bundle. So in this example, you see that A is a project that I wanted, or this voter wanted, and it was also selected by the bundle. B, I wanted, but it was not selected, so I don't get like a unit of satisfaction for this. C is a project that was funded, but I didn't wanted it, so I also don't get anything. And D is a project that I wanted and that was also funded. So then basically I count the number of projects that I wanted, and I approved, and were also funded. And this is the satisfaction that this voter has. And now the problem becomes the problem of trying to find a bundle that will maximize this sum of satisfaction over the voters. So this is one way to define the objective of participatory budgeting aggregation method as an optimization objective, basically, as an optimization algorithm. And basically we found, we consider several definition of satisfaction for individual voters from bundles, and then trying to find the algorithm that will satisfy them. So one way is, as I said before, to just count the number of projects that the voter wanted and were funded by the bundle. This is one possibility, which I call here intersection size. And a different kind of definition would say that the utility of a voter is not the number of projects that were funded and were approved by the voter, but the total cost of those projects. So for example, if the cost of A was $5 and the cost of D was 20, then the satisfaction of this voter could be defined as 25. And this maybe makes sense because the utility of a voter maybe depends on the cost of the project that the voter wanted and were funded or not funded. So this is yet another kind of definition. And the third definition that we consider is what we call binary, which relates to Chamberlain-Courant voting rule that maybe Pallavi talked about in her talk previously, which means that the utility of a voter is either 0 or 1. It's 0 if there is no project that the voter wanted and was funded, and it's 1 if there is at least one project that the voter wanted and was funded. So a voter gets happy, like a complete happy, as soon as there is at least one project that the voter wanted and was funded. So there are different possibilities. So actually, for this last definition of this binary, like 0 or 1 definition, it's fairly easy to see that the problem of trying to maximize to find the bundle that maximizes the total satisfaction as defined like this is NP-hard, so it's hard to compute it because it's just a generalization of Chamberlain-Courant. But for the other algorithms, you could find good algorithms, and okay, this we discussed. Also this, and I think that what is maybe the nicest observation from this study is that basically the greedy algorithm that is used by most cities, this greedy approval algorithm that I discussed before, that basically orders the project by the number of votes that they get, and then go over the list and fund as long as there is money left in the budget. This is basically a greedy algorithm that tries to that can be viewed as an approximation algorithm to trying to maximize the sum of satisfaction when it's defined as the first example of the number of projects that a voter approved and was funded. So this example that I showed before. And it's fairly easy to see that this gives something, I mean, in the minimum, it gives something like 66% approximation for trying to really optimize this satisfaction. And what I think is nice is that actually we don't have to settle for this simple greedy approximation algorithm, because if we also want to really optimize the satisfaction as defined in this way, then this can actually be done. It's not a new algorithm. It's simply you can view this problem as knapsack problem. So say that the size of the knapsack is the total budget that you have to spend, like the total limit in this instance. And now you want to, like in the knapsack problem, you have a set of elements, and each element has some cost and some utility. And now the cost of an element, this is the project, or the cost of an element is the cost of the corresponding project. And the utility of a project that you will put in the knapsack, that you will fund basically, is just the number of voters that approve this project. And now this is really a simple knapsack problem. So knapsack, as I guess most of you know, this is NP-hard problem, but because the maximum utility that you can have for each element is bounded polynomially in the size of the input, basically in the number of voters, then actually this pseudo-polynomial algorithm for knapsack works in polynomial time. So this dynamic programming algorithm for knapsack, here for this instance, it works in polynomial time. So this means that, for example, queries could use not this simplistic greedy approximation to maximizing the total satisfaction of voter were defined as the number of projects that the voter approves and get funded. So instead of using the approximation, it can really optimizes this definition. And in some settings, this will give different result and maybe of higher quality without sacrificing the running time. Basically, this is the bottom line. Okay, maybe this is a good time to ask again if there are any questions so far.
Yeah, is there any question? No question.
Okay, perfect. I mean, I hope that it means that it's understood. If not, please feel free to ask. Okay, if not, then I will continue to. Okay, so far we discussed, basically two algorithms for finding bundles for participatory budgeting, where the voters provide approval ballots, basically where each voter goes to the ballot booth and formally gives like a binary vector over the project, or equivalently just specify a subset of the items or of the project that the voter approves of. And then there are various ways to aggregate those approval ballots, but there are other kind of ballots that may be useful for participatory budgeting. So currently, by far, the most common ballot type is approval, but there are some other ideas, and one of them is ordinal, which means that voters come to the ballot booth and provide permutations or ranking over the project. So a voter comes and say, okay, project P3 is the project that I like the most, then project P7 is the project that I like second, and so on. In the most simplistic setting, voters should come to the ballot booth and provide a linear order over all of the project, but this could be relaxed to providing partial order, or let's say top, like to provide a subset of the project and to rank only these top projects. So now the question is, what can we do where voters submit ordinal preferences? So what are good algorithms to take ordinal ballots and to aggregate them into finding good bundles for participatory budgeting? There are several ideas how to do this, and I want to present one of them. And this algorithm, or this idea, basically lifts the idea of Condorcet. So I guess that you all know about Condorcet or discussed it a little bit. But in the set, I will just remind all of us, so in the setting of single winner elections, the idea of Condorcet was to say that when we want to select a single winner out of from an election, then the best case is that there is some candidate that we can pick, and there is no majority that prefers any other candidate to this candidate that we pick. If you want to view it pictorially, then say that we want to select a president. Let's call this President A, such that there is no other candidate B, such that there is a majority of the population that prefers B over A. Because if this was the case, that there be some other candidate, then we will have riots in the street. I mean, we'll have a revolution, because this majority of the population that prefers B would say that it's not fair that the candidate A was selected, even though there is a majority that wants a different candidate. So in the counter-positive, it means that if there is a candidate such that for no other candidates, there is a majority that prefers this other candidate over this candidate, then this is the candidate that we should pick as a winner for this single winner election, or as a president, for example. So we wanted to lift this idea to participatory budgeting. And how is it, like, the most natural way to do this, I think, is to say, okay, so what is an agreeable bundle, or what is a Condorcet winner for participatory budgeting? There are several ways to define it, but one of them is to say, okay, we want to select a bundle, like a subset of the projects, such that for any other subset of project, there is no majority that prefers this other subset of project to this subset that we selected. And this is for the same reasons, because if now the city says, okay, this is the project that we will fund for the next year, but there is a majority of the residents that come up with a different set of projects, and they said, yeah, I mean, all of us will prefer this other set of projects to the set of projects that the city selected, then this majority of the population could start a revolution, right? Because they don't like the decision of the mayor, basically, of the city. So now, one way to think about it is the following. So on the left, you see the simple explanation of Condorcet idea for single winner elections. So you see on the left this election with 3 voters and 4 candidates, and you can compute this pairwise graph. Basically, each candidate becomes a vertex in this graph, and there is an edge, like a directed edge, between one vertex to the other, if there is a majority of the population that prefers this, like the head of the edge to the tail of the edge. So, for example, there is a directed arc from A to C, because there is a majority of the population that prefers A to C. You can see that indeed V1 prefers A to C, because it ranks it higher, and V2 also prefers A to C. V3 does prefer C to A, but still you have 2 voters that prefer A to C, and only 1 voter that prefers C to A, so there are more voters preferring A to C. then vice versa, and this is why we have an arc from A to C. And in the same way, you can compute this complete tournament. And now, viewing this tournament, the idea of Condorcet says that, okay, if there is a candidate, in this example it's A, that has no incoming arcs, because an incoming arc means, for example, if there was an incoming arc from B, it means that there is a majority, or basically there are more voters preferring B to A than vice versa, and then it's not good, according to Condorcet, to select A. But here you see that A has only outgoing arcs, and then A is the Condorcet winner, because if we select A, then there is no other candidate, B or C or D, for which there is a majority that prefers this other candidate to A. So for single winner elections, to find the Condorcet winner, if it exists, because sometimes it does not exist, it's sufficient to draw this tournament and to look and to see if there is a vertex with only outgoing arcs. And now the one important observation is that this is really simple to do also computationally, because the number of vertices in this tournament is just the number of candidates. So this is linear in the input. And now, okay, we have to do like a quadratic computation to find all of the arcs, but this is still polynomial. And now this is very easy to do and fast. But now our idea of lifting Condorcet idea to budgets was to basically find a bundle, which is a subset of project, for which there is no other project there is no other bundle for which there is a majority that prefers this other bundle to this bundle. And if you now consider this as a tournament, it simply means that you have to draw this tournament, but the vertices of the tournament is all of the bundles that you have. But the exponential or super polynomial number of bundles, so basically the size of this graph is super polynomial. And also in this graph, what you're looking for a vertex that has no incoming arcs. And if there is such a vertex, then the Condorcet idea lifted to participatory budgeting would mean that this is the vertex that we should pick. This should be the bundle that we select. And now indeed, there are actually two problems. So first, you see that if voters provide ordinal preferences, they provide ordinal preferences over the candidates. So basically, they rank the candidates. And now to build this tournament over the bundles, we need first to be able to compute or to infer whether a voter prefers one bundle over the other. So for example, it's easy to see or to be convinced that V1 prefers, say, the bundle AC to the bundle BD, because it prefers A and C, like in total, to B and D, because A and C are ranked above B and D. But it's not clear whether, for example, V1 prefers AD to CB, because A is ranked higher, but D is ranked below. So then we have to come up with some definition of how to lift the ranking that the voter provides over single candidates to ranking of bundles. So there are several ways to do this, and depending on the way that we define it, this will define the tournament over the bundles, as you see on the right, and this will define also the Condorcet winner for this bundles graph. And then still the computational problem is how to find it, because simply going over this tournament will be too time consuming, because there are super polynomial many vertices in this tournament. Okay, and actually, in this walk, what we try to do, we try to find several definitions of this lifting of preferences, and for some of them, we can really find a polynomial time algorithm that find Condorcet winners, if they exist, without going over this full tournament, which have a super polynomial size. So this is one idea of how to do participatory budgeting for ordinal ballots. But actually, after we did this, after we explored this idea, we realized that maybe the idea of Condorcet does not fit well for some of the settings in which participatory budgeting is applied. And this is because Condorcet is very majoritarian kind of an idea. So let me try to explain. Also in the single winner setting, Condorcet is majoritarian in the sense that if there is so say that you have a population of 100 voters. Now if there are 51 voters that want something specific, then it doesn't matter what the other 49 minority of the population want, because this majority basically controls everything. And this is because Condorcet is inherently very majoritarian kind of an idea. Maybe this is easier to explain in participatory budgeting. So consider, for example, that you have in one city 2 neighborhoods. One of the neighborhoods contains 60% of the population, and the other neighborhood contains 40% of the population. And let's say that there are some projects suggested or proposed in the first neighborhood that contains 60% of the population, and some other projects suggested or proposed in the other neighborhood that contains 40% of the population. And now let's assume that each voter that lives in a neighborhood approves only the project that are proposed in her neighborhood, because people want projects that are close to the place that they live in. So if there is a project of building a school, then I will want it if it's in my neighborhood, but not if it's in the other neighborhood. And now if you think about this Condorcet idea, basically all of the voters in this 60% neighborhood will approve all of the projects in this neighborhood. So each of the projects in the first neighborhood will get 60% of the votes. And similarly, each of the projects in the second neighborhood will get 40% of the votes. And now basically only projects from the first neighborhood will get funded, because there is no majority to decide other way. It's also good to note, I think also important to note, that also this greedy algorithm and also this utilitarian algorithm that I described before, that basically tries to maximize the total satisfaction defined as the number of projects that the voter approves and get funded. All these algorithms basically will select only projects from this one neighborhood. And I think that in the setting of participatory budgeting, at least as it applied in cities, this is not very desirable, because it means that basically all of the population of the city will pay taxes to the city, but the city will use these taxes only to fund projects in one of the neighborhoods. And this is a consequence of the majoritarian way in which this utilitarian approach works, and also this Condorcet approach works. And to basically overcome this limitation or this undesired effect, what we thought is that it makes sense to try to find algorithms that are more proportional. And there are several ways to try to design such algorithm. And first, we use the axiomatic approach, which means that we try to formalize what does it mean for an algorithm to be proportional in the setting of participatory budgeting. And then if we now are able to define mathematically what is a proportional algorithm, or what is a proportional participatory budgeting algorithm, then we can start to look for an algorithm that satisfies this property. So basically, we try to capture what does it mean for an algorithm to be proportional. And the first observation is that, for example, consider this example of 2 neighborhoods with 60% of the population here and 40% of the population in the other neighborhood. So we thought that a proportional algorithm should basically spend the budget proportionally. So it should spend 60% of the budget into funding projects in one of the neighborhoods, in the first neighborhood, and spend the remaining 40% of the budget in funding project in the second neighborhood. Another question is how to take this intuition of what is a proportional algorithm and find a formal definition of an axiom or a property that now algorithms could be compared based on whether they satisfy the property or not satisfy the property. And this is what we try to do in this paper. Basically, we said, okay, in many settings of participatory budgeting, it's crucial that the algorithm will be proportional. Okay, so in this paper, we consider approval-based elections. And for this kind of election in which voters give approval ballots, we came up with several algorithms that try to capture the idea of proportionality. And one of them is written here on the left, axiom 1. It also lifts axioms for finding proportional parliaments or proportional committees in multi-winner voting, but for the setting of participatory budgeting. And let me try to explain like the flavor of these proportional axioms. So one of them is written here, as I said. It basically says that a proportional algorithm is such that shall satisfy the following. So for each kind of preference profile, meaning for each kind of population with votes, it should satisfy the following, that now each group of voters that is sufficiently large, so contains a significant portion of the population of the voters, and also they are somehow coherent. So each kind of basically a population minority, which is a minority that is big enough and also coherent enough, shall get some kind of representation in the bundle that the algorithm selects. And more formally, it means that each group of voters, V prime, that contains at least N over L. So N is the number of votes, and L is the total budget. So basically, it means that, for example, if there is a big minority is such that if you consider only this minority out of the total budget, they basically shall correspond to at least something. So at least like N over L of the budget. So for example, at 10% of the population, should be enough. And so this is one thing, that this population, this minority should be big enough. And the second thing is that they should be coherent. And the way we formalize that, they should have some non-empty intersection, meaning that there is at least one project that all of these minority voters want. So for example, if there is a 10% of the population, that all of them want some school. And now this 10% is big enough, and they are somehow coherent. So this is not acceptable to the voting rule if it does not select to the output bundle any of the project that this 10% minority wants. So this axiom is very, so in one sense it's very strong because it considers any kind of minority that should have at least some non-empty intersection, so at least one project that all of them want. And it means that each kind of these minorities cannot be fully ignored by the algorithm. So this is strong in this setting, but it's quite weak in the sense that it means that even if there is a minority of, let's say, 40%, then this doesn't mean that this minority of 40% should get at least 40% of the funds. It just means that it should not be completely ignored. So at least one of the projects that one of these voters from this minority should be funded. It could be that basically a 40% minority gets just one project that costs $1, and now this axiom will be satisfied. So the axiom is quite weak in this sense. But still, I mean, it's fairly easy to see that all of the algorithms that we considered before, these algorithms that depend on the satisfaction values and on the Condorcet criterion, they fail this very simple axiom. So in this sense, this axiom really captured some aspects of proportionality, and it shows that really the other voting rules are not proportional, but they are majoritarian. So they do not respect minorities in a very weak sense even. And now the question is whether there are algorithms that respect this kind of axioms, and we could find out some of them. So basically this depends on, so here I showed you only one axiom, but there are other similar axioms with different flavors that we also played with. And For some of them, we could show that basically there is no polytime algorithm that satisfies this kind of axiom. And intuitively, this is because for an algorithm to satisfy this kind of axioms, it should intuitively go over all of the possible voter groups, basically all of the possible minorities, but there are super polynomial many minorities, because if you have n voters, then you have to do the n possible subset of voters, and each one of them you should see whether it's big enough and whether it has some non-empty intersection. So this is, I mean, if you do this really simplistic, then you have to do this super polynomial amount of work. But still, for some kind of definitions, you don't really have to go over all of the voter groups, but you can simply have usually some kind of an iterative algorithm that go over the voters and fund projects, and we could prove that it satisfies these kind of axioms. What I think is the nicest axiom, the nicest algorithm is an algorithm that builds upon ideas of Fragment. You see here the picture of Edward Fragment, was a Swedish person from maybe 150 years ago. He came up with, I think, a nice algorithm for selecting parliament, and we lifted this idea for selecting bundles, and very, very simple, not quite accurate, but almost accurate definition of the voting rule goes as follow. So think about all of the projects that you have, and each one of the project has some cost. And now think about the voters, and each voter basically supports several projects. So for example, if I approve project A, C, and D, then I support them. But now this algorithm works in the following way. So imagine that each voter has a bank account, and initially this bank account has only $0. And now what is being done is that continuously in time, these bank accounts of all of the voters get filled with money. So this is like a continuous money. So so it's not time step, but it's continuous. So continuously in time, the money that each voter has grows, and it keeps growing until something happens. And what happens is that there is one project such that the money that all of the voters that approve this project is sufficient to fund this project. So for example, if there is a project that costs $3 and there are 6 voters that approve this project, so when the bank accounts of each one of them will have $0.50, then jointly these 6 voters could fund this project. So the algorithm will stop after filling all of the bank accounts in $0.50, and then it will use this money to fund this project, and it will still keep all of the bank accounts of the other voters with $0.50, but it will take the money from the bank accounts of those voters that now funded this project. And now the algorithm continues, and because basically these voters that used the money to buy this project, they are already somehow satisfied also in the context of this axiom, because this minority of voters that wanted this project, they already are not fully ignored, because there is at least one project that they wanted and got funded. And now we continue, then basically we could show that this kind of infinite bank or continuous bank accounts filling algorithm that works on the ideas from Ben really satisfy this kind of proportional axioms, which means that it could really achieve proportional bundles. So this is really a different kind of an algorithm that has different properties than the other algorithm, because it selects proportional bundles and not majoritarian bundles. So this is one algorithm that achieves this proportionality kind of axioms. The other algorithms that were suggested by us and by others, and I know that some people in the community try to speak, including me, try to speak with municipalities to try to convince them to shift the process from these majoritarian processes that they use currently to more proportional processes like this one that builds upon the ideas fragment. Okay. Any questions so far?
Hi, Nimrod, can you hear me?
Yeah, sure. Thanks.
So I have a question about the Condorcet winners part.
Yeah.
So did you say that for certain preference extensions from individual projects to bundles of projects, the Condorcet problem was hard? Did you say? Maybe I missed it.
Yeah. So what I say is that we tried several set extensions, basically lifting preference over individual candidates to preference over bundles. If I recall correctly, for some of them the problem was NP-hard, and for some of them we could find polynomial time algorithm. If I remember correctly, the set extension that we found that we consider last and was polynomial to compute Condorcet winners according to this set extension was that basically we do the set extension lexicographically. So it's almost like border. I mean, you or put differently, a voter prefers one bundle to the other if the most preferred candidate in one is better than the other, and if they are equal, then you go to the second, and so on and so forth. And for this lexicographic set extension, I think that you can basically populate the winning bundle iteratively without going over the super polynomial tournament. And therefore,
I
you
see.
get polynomial algorithm.
I see. And have people also studied a setting where you look at a budget division that does not lose out to too many other budget divisions? So it's okay for budget division to lose some, but hopefully not too many.
Let me see that I understand. You mean not finding a Condorcet winner that has only, I mean, that has no incoming arcs, but finding a bundle that has mostly outgoing, but not too many.
Yeah,
Not too many.
It's a candidate that loses very few of its head-to-head elections.
Yeah, I see. Yeah, so this would be corresponding to, for example, Copeland voting rule for single winner. That basically, right? As far as I recall, there is no work about this. There are no works about it.
I see.
So this is very reasonable and natural, but I think that there is nothing done on it.
I see. Okay, thanks.
Okay, perfect. Yeah, thanks for the questions. Okay, so let me continue to another idea.
Sorry, I have also
Sure. Yeah, sure.
In the context of coalition formation, there is this concept of master lists. My question is whether it can be used also in the proportionality and in the context of participatory budgeting.
Sorry, I just couldn't hear the name of the concept that you referred to.
Master lists.
I'm not sure I'm familiar with it. Do you want to explain it or?
Okay, there are multiple master lists which are relations between these projects, and if we can derive, if we have two agents and preferences of each agent can be derived from this master list, like preference is subset of this master list, then we say that both of them have same corresponds to same master list.
Okay, so I don't know. I mean, we can discuss it maybe later, but I'm not familiar with this notion.
Okay. Thank you.
Yeah. Any other questions?
No, sir.
Okay, thanks. Okay, so let me continue to yet a different idea of how to design algorithms for participatory budgeting. And here, basically, we started from the idea of maybe changing the elicitation or the ballot type. So as I described before, the most popular ballot type is that people come to the ballot booth and they select the project that they want. Usually this comes with some limits. So for example, in Poland or in Warsaw, if I remember correctly, people come to the ballot booth and they select at most 10 projects. And in Cambridge, the example that we saw before, people come to the ballot booth and select at most 5, but all of these are approval ballots. And in the Condorcet context, we describe ordinal ballots, and yet a different kind of ballot that somehow felt to us very natural for participatory budgeting is what usually is termed cumulative ballots. The simplest way to describe it is that basically people come to the ballot booth and each one of them gets like a virtual coin, and they should split this virtual coin among the projects. So basically, instead of simply giving a binary decision on each of the projects, or simply approving or disapproving each of the projects, like in approval ballots and the example on the left, people split this one unit of preference into several projects. So in this example, this voter put support intensity of 0.2 into this project, and support intensity of 0.5 into this project, and support intensity of 0.3 on this third project, and no support for the other project. So it's like 0 for all of the other, which so formally this just means that if you have M project, then the ballot or the preference of each voter is just a vector of M entries, but not a binary vector, but a vector in which there are numbers or values in each one of the entries, and the sum of values in the vector is 1. So basically splitting this unit of preferences among the project, which from a voter point of view, this gives more expressive power to the voters, because on the left you just see that the voter likes these 3 projects, but you don't know, or maybe the aggregation algorithm does not know which of the project the voter likes more than the other, or what is the intensity of preference, just this binary division. But on the right, you see that actually this project really likes this project, that because she give 0.5 intensity of preference and so on, which is more than this 0.3 and more than this 0.2. And so this is one reason why maybe cumulative ballots could be better, at least for some voters, because it gives more expressive power or flexibility to the voter. And somehow very intuitively, in participatory budgeting, the problem that the city deals with, or the process, is basically how to take like a global money and split it among the project. And cumulative ballots really does it, right? Because people really take the money and this virtual coin, and they split it among the project. So this is why we thought that maybe cumulative ballots make sense for participatory budgeting. And then we started to think about how to aggregate ballots that are cumulative ballots. So basically, what is a good algorithm that takes n ballots that looks like this, so n cumulative ballots, and output a winning bundle. And for these are some ideas, and one of them I want to show here. And it works as follows. It basically takes its intuition or its general idea from a single winner voting rule that calls STV. I'm not sure if Pallavi talked about it, but STV stands for single transferable vote, also sometimes called the alternative vote. But I will not explain this STV rule, just I wanted to mention that this algorithm takes the inspiration from, or basically generalizes and modifies this algorithm to the setting of participatory budgeting for cumulative ballots. But let me just explain this algorithm. So it works as follows. So basically, each voter, as I said before, provides a vector that sums up to 1. But it's useful to think about this vector basically to normalize it into L over N. So let's say that the total budget limit is L. So in the example of Paris, this is, last year it was 100 million euros. So L is 100 million euros. And now if you have, let's say, 100 voters, or let's say we have 1 million voters, then intuitively each one of the voters controls L over N of the total budget. So each one of these million voters should control 100 million over $1 million, which is just 100 million. So we can just look at these cumulative ballots and normalize them basically to multiply them, all of these values by L over N, which is almost like saying that instead of giving each voter just one virtual coin, we give each voter L over N virtual coins, and this voter should split these tokens among the project. This is just the way that I think is useful to view the ballot that we get for the description of this algorithm. Okay, so this is what voters basically get, and now voters split these each voter splits the L over N tokens that they have among the project. So in this toy example, we have 4 projects: this school, hospital, police, and fire department. And so, for example, this voter, if she gave 0.2 support intensity for school and 0.8 intensity for hospital, now after this normalization, it basically means that she gave 20% of these L over N tokens that she had into this project, and the remaining 80% here. So if L over N is 100, it means that this voter basically gave 20 tokens to school and 80 tokens to hospital. And now I think it's useful to visualize, at least for me, to visualize these glasses for each of the projects. So each project, imagine a glass where the height of the glass is just the cost of the project. So if school cost $1,000, then this will be a glass that can contain exactly 1,000 coins. And now this voter basically put 20 coins in the glass of school and 80 coins in the glass of hospital. And this is what all of the voters pictorially do. They basically get L over N tokens from the city, and they split these tokens among the glasses of the project. And now basically what we have, we can start the algorithm, and the algorithm starts where we are looking at the glasses. So some of the glasses will be empty. So for example, if no voter gave any support to school, then this glass will be empty. Some of the glasses will be half empty or half full, depending on how you want to see this, but they will not be empty and they will not be full, corresponding to project that some voters liked, or maybe even all of them supported, but it didn't get total support, which is basically the total support that they got, or the total number of tokens that they got from voters is still smaller than the cost of the project. And then this will be like a half full glass for a project. And some of the project will be full and maybe even over full, with some money like dripping from the sides, corresponding to project in which the total tokens that they got from voters is more than the cost of the project. Okay, so now how does the algorithm take these glasses, pictures, and decides which project to fund? It does so in the following way. So it does so iteratively. In the beginning, no projects are yet funded. And now in each iteration, the algorithm tries to find a project whose glass is full, or maybe even with some excess. So in this example, this is maybe the police. And now it decides to fund this project. So it takes basically the tokens that were put by the voters that correspond to the cost of the project police. And it says, okay, police is now funded, but now maybe there is some excess tokens. And these excess tokens, we want to bring them back to the voters in proportional to the amount of tokens that each one of the voters gave. And now basically split those excess tokens and give them back to other projects. So for example, if this voter gave 20% of the tokens, then we want this voter to get back 20% of the excess tokens. And now if this voter besides giving some tokens to police, it gave, let's say, half of the remaining intensity for school and half for hospital. Now we take these 20 tokens that we got back to this voter, 10 of them we put in school and 10 of them we put in hospital. So we don't want to throw to waste these excess tokens, but we want to move them proportional to the other projects. And now we reiterate, if there is now yet another, so now maybe the hospital before was not full, but now maybe it is full. So now we fund it and we do the same. And the different thing that could happen in the algorithm is that maybe now there is no project that is full, that his glass is full or in excess. So now we pick the project which is the least full, that has the least amount of tokens, and we basically say, okay, this project will not get funded, and we take the XX token and we also distribute it to the other projects proportionally as we did before, and we reiterate until we are out of budget. There are no more projects that can fit into the bundle without going over the budget. So this is the idea of the algorithm. Basically, in iterations, in each iteration, either we eliminate a project and we take the tokens that were originally given to this project proportional to the other project, hoping that some of them now will get full. But if in some iteration there is one project at least that is full, then we take this project, we fund it, and we also move the excess tokens to the other projects. So this is how this algorithm works, or let's say that this general idea, because there are some decisions that have to be made. Most importantly, for example, if there are several projects that are full, which one of them we select, and also if there are how we order the project by the fraction of fullness that the glasses have. But there are some variants, but this is like the general idea. So actually, we could prove that this algorithm really satisfies some variants of this proportional axiom, as I showed before. And then actually we ran some experiments because we got data from some elections in Poland, most of them from Warsaw, but also from other places. And we ran them, and basically we took the ballots that voters provided for the city, like real ballots. We ran the aggregation method that is used in Warsaw, which is this greedy approval, and we also ran this kind of glasses algorithm. And indeed, we got different results. The total happiness, like the total utility or satisfaction that this algorithm gives, is of course lower than you get if you try to directly optimize for this from using this knapsack algorithm from before. But still, we could show that we get a very good approximation to this total satisfaction, while getting this property of proportionality, which we don't get otherwise. So somehow there is a trade-off between maximizing the social welfare or the satisfaction and being proportional. And from experiment, it seems that these algorithms give a nice trade-off between these two desires. Okay. So we don't have too much time. Maybe, again, this is a good time for question if you have for this last algorithm. Okay, if not, that I just want to mention, sorry.
Hi, just one question.
Yeah, sure.
So, when we're distributing the tokens to all the voters, like each voter gets an L over N tokens and they sort of split it across all the projects. So, doesn't that involve some sort of estimation on the voter side about what the project costs will be? Because they'll have to split it accordingly. Because otherwise, there's a chance that there'll be a huge discrepancy among the projects they like, which get overfunded or underfunded, because they might underestimate or overestimate the costs and
I
split
see.
it.
Okay, so I think that your question is combined of several aspects which are relevant. Okay, so one of them is that, I mean, the standard setting is that all of the voters know the cost of all of the projects. So, for example, I will go back. Okay, even here you can see that each of the project has this price tag in the description of the project. So voters really know what is the cost of each of the project, and this I think is useful and crucial, because I mean it's hard for voters to say whether they want to build a stadium if they don't know whether this stadium will cost $10 or $12 billion, right? Because it should have some effect on the preferences of voters. So this is something that voters know, at least in the model they know it perfectly, but also in reality. So people propose projects and the city gives exact price tag on each of the projects. And so this is one aspect. And the second, I think, if I understood from your question, is that there is some kind of an implicit collaboration between voters, because my decision of how much tokens to give to, or basically what values of intensity, like this 2.2 or 0.3 or 0.5 to give to each project, maybe depends on the preferences and the submitted ballots of the other voters. So, I mean, this is always the case. I mean, in any kind of ballot type and in any kind of algorithm, not all of them, but in all of the reasonable ones. And this is also the reason why in all of the reasonable algorithms, there is the possibility of strategic voting. So if I know what the other will do, maybe I should provide a different ballot than the ballot that I really have in my heart, because this will be better for me eventually, given the operation of the algorithm, the other voters. So this is something that cannot be avoided, and this Gilbert-Satterthwaite theorem shows this. And the third thing that I wanted to comment is that I think that the nicest property of this algorithm that I presented here, is that, so say that I want this fire department, it's very important for me, but I'm not sure whether other voters like it. I mean, I'm not sure how popular it is, and even worse than this, I know that this is not a very popular project. So if we would use this approval method that is used in Warsaw and in Paris, that I have to select only 10 projects and cross them, it basically means that I have like a budget of 10 tokens and I need to split them, but I cannot only put one token in each of the projects. Then I will be quite afraid to put one of the tokens in the fire department, because I would be afraid that there will not be enough support for this, and then this token will get burned, like get destroyed. So this is true for this greedy approval method that I showed before, that is like the most popular method, but this is actually not true for this glasses algorithm, because even if I put some tokens on the fire department, then it could be the case that indeed the fire department will not get enough support, but these tokens in the glass of the fire department, containing also my tokens, will not get burned. In one of the iterations, maybe after police will get funded and hospital get funded, still maybe now after those iterations, no project will get enough support, and now maybe the fire department project will get destroyed, but the tokens that are there, basically the water in the glass, will get back. I mean, they will not really get back, but the operation of the algorithm imitates the procedure in which the tokens get back to me also, to all of the supporting voters, and now we redistribute them to the other projects. And in this way, basically, even if I like the fire department and I don't think that it will get enough support, still I could put my support there without being afraid that this support will get banned and not used eventually. Okay, so I hope that this answered the question. Let me just finish with some other considerations that are relevant to participatory budgeting. So basically, until now, we considered the standard model of indivisible participatory budgeting, in which we have a set of projects, and the projects are not connected or do not have any other properties or consideration other than the cost of the project. And we have voters that provide the preferences by approval or ordinal or cumulative. And we have some budget limit, and we want to find a good algorithm, a good aggregation algorithm. And this is, as I said, this is by like the standard real-world model of participatory budgeting. But if we think about it a little longer, then you see that this model is also somehow limiting in several aspects. And what I want to present now is several ideas on how to generalize the model of participatory budgeting to be able to provide algorithms that take these aspects, these more generalized and involved aspects into consideration. So one of them is what we try to do here in this paper. Basically, we started from the observation that maybe there are some projects that has some connection or they are not really independent. So for example, if there is one project to fund the school, this is project 1, and project 2 is to build a bus stop next to the place in which this school should be built, then maybe I really want that the city will build the school there, but I don't want that the city will build the school with no bus stop. And also vice versa. I mean, I don't want the city to build a bus stop and not build a school because there is no point in this. So I will basically not be happy if the school will get funded and the bus stop will not, or the bus stop will be funded and the school will not. So only if one of them will get funded, but I will be very happy if both will be funded. And so this means that there is some relation or some synergy or some connection and dependence between projects in the participatory budgeting process. And we try to formalize this notion and to see whether we can come up with good algorithms that take these relations between projects also into account. And the way we thought about it is the following. So let's say that these are the 10 projects that we have in the instance. For example, P9 is the school, and P10 is the bus stop next to the school, and these are some other 8 projects. And let's say that these 10 projects, now we can divide them into groups, such that in each group, the project in the group has some dependence. So for example, we would group P9 and P10 into one group, because as we said before, the satisfaction that voters will get from projects that are funded in this group are dependent on the other projects. And in particular, say that I am this voter from before. So if P9 and P10 will not get funded, then I will not get any utility. If P9 then will get funded and P10 will not, or the other way around, that P10 will get funded and P9 not, then I will get also no satisfaction, because I will only get satisfaction if both projects from this group will get funded. So this means that a simple way to model is to say that, okay, my satisfaction from projects in this part is 0 if there are no project funded, is still 0 if there are one project funded, but it's, let's say, 1 if 2 projects get funded. And now, putting this more generally, now we can define the function for each one of the parts, which could be superlinear or sublinear, and could correspond to the utility that voters will get from specific number of projects that get funded from each one of the parts. And now the question is whether we can now maximize the total happiness that voters have from bundles of this instance, where the utility of the voters is defined using these interaction functions. This function that takes into account not just the number of projects that get funded, but from which part they get funded, and how many projects from each part are get funded. And this is not, this could be not linear in the number of projects. And this really can capture at least a simple variant of connection between voters. Okay, so for this problem basically that generalizes the standard model of participatory budgeting, it's not very hard to see that it's NP-hard in general, but we can find really, I think, useful approximation algorithms and parameterizations, and also some domain restrictions on which function we allow. And that for this restriction, we can really have polynomial time algorithms. So this is one direction to generalize participatory budgeting to be more expressive. And yet another idea was to also consider groups, but not consider like the superlinear or sublinear utility from number of projects that get funded in each group, but to consider that this grouping corresponds to, let's say, different neighborhoods or different thematic subjects. Like you can take all of the project and say, okay, these projects are projects that relate to infrastructure, these projects relate to education, these projects relate to culture, and now maybe you want to define certain lower bounds or upper bounds on how much of the total budget you want to spend in each one of the districts or in each one of the thematic subjects. And this also generalizes the model of participatory budgeting. And for this also, this problem becomes fairly quick, becomes NP-hard. But for some restrictions, we could show exact and approximated algorithms. What I think is the nicest is that actually if the division into districts is hierarchical, so basically you take a district and then you take neighborhoods and streets and so on, and you define lower bounds for each one of these geographic group or place or region, then basically we can do this without any computational cost. So we can go over this hierarchical division of the projects into groups, and still we can do this in polynomial time. Okay, so there are some further ideas, but maybe this is a good time to conclude. So what I think is the state of the art in participatory budgeting, basically you have to select the elicitation method or the ballot type. I still believe that cumulative ballots are very reasonable for budgeting, but this is maybe also a matter of taste. Then you have to choose the aggregation method. And I think that it really makes sense to pick an aggregation method that at least optimizes some stuff and not just approximation or grid approximation to this. And also it should be something proportional. And also I think it's good to know that these algorithms can be polynomial time and still deal with some forms of project interactions and diversity constraints. And there are also some ideas on how to allow voter delegation, but I didn't spoke about it. And I think that if we really can come up with good algorithms and we can deploy them in the real world, then this can really make a nice impact into societies in cities that use participatory budgeting. Thank you very much.
Thanks, Nimrod. Is there any question? No, there's no more question. Yeah, there's one question.
Now I stopped sharing so I can see you.
Hi, Nimrod. Can you hear me?
Yes?
So, in that, under aggregation method, have people studied ways to give, say, weighted preferences to certain groups, especially when it comes to making public utility projects? Maybe some communities are underserved historically, and we want to sort of give their preferences a little higher weightage. So what kind of voting rules would that be?
I see. Yeah, okay. So what I discussed today is basically like one person, one vote, right? So the weight of the voters are uniform. There are some works that goes into maybe different variants of what you suggested. Which of you generally is basically how to do weighted voting for participatory budgeting. So each voter can have different weight, not just unit weight. Something that comes to mind is that actually participatory budgeting is used quite frequently in blockchain worlds, in decentralized organizations. And there basically people vote not with, they really vote with tokens. So basically people that have more money, they have more say. This is one way to wait, but maybe this is not really what you wanted, because you wanted actually like the other way around. You wanted to give more support to the underrepresented people. And there are some ideas on how to do this. There are some works that tries to do basically budgeting with philanthropes, basically how to aggregate like the preferences of philanthropes together with preferences of people. And also in the context of blockchain, there are some ideas on how to basically equalize the, the society wealth using this kind of participatory budgeting ideas. So this is like the general, and practically algorithmic wise, I mean, you can view a voter with more weight as several voters and do the same. And the algorithm will go through. It's not clear whether this is the optimal way to include weights into participatory budgeting algorithms.
Thank you.
Any other question? So thanks a lot. See you tomorrow.
Yeah, thanks. Thanks, Pallavi, for the invitation, and see you tomorrow, I guess.
See you. Bye.
Bye-bye.
Bye. So we have 20 minutes break now.